The semiconductor shock. What happens if Taiwan's chip production stops? If the world's most advanced semiconductor factories stopped operating tomorrow, the shock would not begin on a battlefield. It would begin in factories, server rooms, car plants, and data centers. Modern civilization runs on chips, and the most advanced chips are not produced everywhere. They are highly concentrated. So what happens if Taiwan's advanced semiconductor production goes offline? Not for a day, not for a news cycle, but for weeks, months, or longer. This is not a prediction. It is a systems stress test. For decades, semiconductor manufacturing has become more specialized, more capital-intensive, and more geographically concentrated. Design, fabrication, equipment, materials, and packaging are distributed globally. But the most advanced logic chips, the processors that power cutting-edge smartphones, high-performance computing, AI accelerators, and advanced defense systems, are produced in a very small number of fabrication facilities. A significant share of that advanced capacity is located in Taiwan. These facilities do not just produce chips for one country. They manufacture for global technology firms. American companies design processors. European firms integrate them into industrial systems. Asian manufacturers assemble finished products. Data centers worldwide depend on a steady flow of advanced silicon. It is one of the most complex supply chains ever built. Now imagine that production halts. No new wafers leaving advanced fabrication lines. No shipments of high-end processors. No new supply entering global distribution channels. Let's break down the impact in phases. Phase 1. Immediate market reaction. Within hours of a confirmed halt in advanced production, financial markets would react. Technology stocks would experience sharp volatility. Semiconductor designers that rely on external manufacturing would see their share prices move rapidly. Automotive companies with tight chip inventories would face uncertainty. Cloud computing providers and AI hardware firms would be reassessed by investors. Insurance markets would adjust risk exposure. Supply chain managers would activate contingency planning. But the physical world would not change immediately. That's because semiconductor supply chains operate on inventory buffers. Distributors, manufacturers, and system integrators hold stock. Some sectors carry weeks of supply, others carry less. The shock begins in pricing and expectations before it begins in factories. Phase 2, 30 days. After roughly a month without new advanced chips entering the system, pressure becomes tangible. Automotive production is one of the first sectors to feel it. Modern vehicles contain hundreds, sometimes thousands, of semiconductor components. During recent supply disruptions, automakers were forced to idle production lines due to missing microcontrollers. Without replenishment of advanced processors, manufacturers prioritize high-margin models. Production slows. Delivery times lengthen. Consumer electronics follow. Smartphone launches may be delayed. Laptop inventories tighten. Gaming consoles become harder to source. Prices rise gradually, not instantly. Cloud service providers begin rationing expansion. Data centers still operate. Servers already installed continue running. But plans to expand capacity slow if advanced processors cannot be secured. AI training clusters, which rely on specialized high-performance chips, face constraints. Research timelines extend. Technology roadmaps adjust. Industries dependent on precision industrial equipment feel secondary effects. Machine tools, robotics, telecommunications infrastructure all depend on sophisticated semiconductor inputs. It becomes a question of allocation. Who gets priority access to limited supply? Phase 3, 90 days. After 3 months, the shock becomes structural. Inventory buffers deplete. Manufacturers exhaust alternative sourcing strategies. Older generation chips cannot simply substitute for advanced processors in many applications. Defense procurement becomes a concern. Modern military systems, communications, radar, guided munitions, secure computing depend on advanced semiconductor technologies. Strategic stockpiles exist, but long-term sustainment requires ongoing production. Energy infrastructure also depends on electronics. Grid management systems, smart meters, renewable energy inverters, and advanced battery systems rely on semiconductors. Upgrades and maintenance slow. Medical devices, including advanced imaging equipment and life support systems, require reliable electronic components. Production bottlenecks could emerge in specialized equipment. At this stage, governments intervene more visibly. Export controls tighten further. Strategic reserves are assessed. Emergency industrial policies accelerate. Incentives for domestic fabrication expansion intensify. But semiconductor fabrication is not easily scaled overnight. Building an advanced fabrication facility costs tens of billions of dollars and requires years of construction, equipment installation, and process calibration. The ecosystem includes suppliers of extreme ultraviolet lithography equipment, specialty chemicals, precision manufacturing tools, and highly trained engineers. The system cannot be rebuilt in months. Phase 4, 1 year. If advanced production remains offline for a year, the global technology landscape shifts. Technology innovation slows. Product cycles extend. Companies redesign hardware to function on less advanced nodes where possible. Efficiency declines. Artificial intelligence development faces hardware constraints. Cloud expansion slows. Edge computing devices are redesigned. Automotive manufacturers simplify electronic architectures. Consumer device makers lengthen replacement cycles. Geopolitically, pressure increases dramatically. Countries accelerate industrial policy programs. Alliances strengthen around semiconductor supply security. Strategic competition intensifies over equipment, materials, and engineering talent. The shock would not resemble a traditional financial crisis. It would resemble a slow industrial constriction. Modern economies would not collapse overnight, but growth would decelerate. Investment would reallocate. Innovation timelines would stretch, and geopolitical calculations would shift. Why is this system so sensitive? Because semiconductor manufacturing has evolved toward extreme specialization. Design firms are often separate from fabrication facilities. Equipment suppliers are highly concentrated. Certain lithography technologies are produced by only a handful of companies globally. Materials supply chains span continents. Efficiency drove this structure. Concentration increased productivity, reduced cost, and enabled rapid technological advancement. But concentration also creates choke points, and choke points create leverage. The semiconductor ecosystem is not fragile in the sense of being weak. It is fragile in the sense of being tightly coupled. When a tightly coupled system loses a central node, adjustment is possible, but not instantaneous. The United States, Europe, Japan, and other economies are investing heavily in domestic semiconductor capacity. Fabrication plants are being built. Subsidies are being deployed. Strategic stockpiles are discussed. But even with accelerated investment, replicating the full scale and maturity of advanced manufacturing capacity takes time. The question is not whether alternatives exist. The question is how long adaptation takes, and at what cost. This is not simply a Taiwan story. It is a story about how modern power is embedded in infrastructure. Semiconductors are the foundation of artificial intelligence, defense systems, telecommunications, automotive production, energy grids, financial data centers, consumer electronics. They are the nervous system of the global economy. When we talk about geopolitical risk in East Asia, we are not only talking about territory. We are talking about supply chains that underpin modern industrial civilization. And that is why semiconductor concentration matters. The semiconductor shock scenario reveals something deeper. Power in the modern world is not just measured in military size or GDP. It is measured in control over indispensable nodes. In previous eras, those nodes were canals, oil fields, and sea lanes. Today, they include fabrication plants, lithography machines, rare materials, and advanced manufacturing talent. If Taiwan's advanced semiconductor production stopped, the world would not go dark. But innovation would slow, manufacturing would strain, defense planning would adjust, markets would reprice risk, and industrial policy would accelerate dramatically. The lesson is not inevitability. The lesson is interdependence. Modern prosperity is built on systems that cross borders. Understanding those systems is essential to understanding global stability. What to watch next? As nations race to secure semiconductor independence, the geography of technology power is quietly being redrawn. and the consequences will shape the next decade of economic and geopolitical competition. If you want to understand the systems behind global power, subscribe to Systems Watch. Thank you for watching.